In lesson 2, we're going to continue solving some polynomial equations, and we're going to look at some new methods, one called the square root method and one called completing the square. So basically, the square root method is going to occur whenever you are missing that middle term. So whenever, if you have your equation ax squared plus bx plus c equals 0, and this middle term is missing, we're going to be able to do the square root method. So the square root method is kind of like a shortcut. Instead of having to factor, what you can do is you can apply this square root method, which means you're going to take the square root of both sides. Whenever you have some quantity being squared set equal to a number, meaning that middle term bx is missing, you can take the square root of both sides and solve it that way. So for example, this first um, equation here, if I solved it by factoring, what would happen is we would have to set it equal to 0. So I would have x squared minus 16 equals 0. And then I know it's a quadratic and it's a difference of perfect squares, so I would square root both sides and I would have opposite signs for the factors. And then I would split it and set each piece equal to 0. Since it's two pieces being multiplied to equal 0, one of them has to equal 0. And I would solve it. I would get x equals -4 or x equals 4 as my two solutions. Now the new method, the square root method, is a little bit quicker because since we're missing that middle term, you can simply just take x squared equals 16 and you can square root both sides. If you square root x squared, it's just going to be x. And if you square root 16, it's going to give you 4. However, one thing that you have to remember with this method is that your solution is always going to be a positive and a negative of whatever you square rooted, because you started off with a variable being squared. So if you look at this original equation, I started off with x being squared. I don't know what x is, so I have to give all the possibilities for x. So x could equal -4, because if you square -4, you get 16. X could equal +4, because if I square +4, I'm going to get 16. So that's why you're always going to have your two solutions, your plus or minus, whenever you're square rooting a variable. And again, these two solutions should match, because it's just two different ways to solve the same equation. So the square root method uses this property down here that whenever you have a squared equals b, b is some real number, then a is going to equal the square root of b, and a is going to equal the negative square root of b. So essentially a equals plus or minus the square root of b, because you don't know if a was a negative number or a positive number to start, and both positive and negative would satisfy the original equation. So we can apply this method to other examples. So if you look at this next example, I still have a quantity being squared set equal to a number. So that means I can do the same exact thing where I take the square root of both sides and the squared terms cancel. So I have 2x minus 3 is what's left, equals plus or minus, because there was a variable in there, 5 when you take the square root of 25. And then you just solve this for x. So I would bring the 3 over. So I would have 2x equals +3 plus or minus 5. Then we would divide everything by 2. So we get x equals 3 plus or minus 5 over 2. And essentially what happens now is you have two cases. You have 3 plus 5 over 2, and you have 3 minus 5 over 2. So since these are all whole numbers, we can actually combine them. So 3 plus 5 gives me 8 over 2, which gives me 4. 3 minus 5 gives me -2 over 2, which gives me -1. So here are your two solutions. Now, if you wanted to try doing this by factoring, what you would have to do is you would have to do the square and do 2x minus 3 times 2x minus 3. And then you would subtract over the 25, set it equal to 0, and then solve it that way. This square root method is much shorter because we can just use the quantity being squared and take the square root of both sides. So let's look at another example of this. This we're kind of just throwing back in imaginary numbers, and the reason for that is when you look at this example, when I take the square root of both sides, you can see that I'm going to have an imaginary number because I'm taking the square root of negative 12. So just to refresh your memory, to simplify this, what you would do is you first are going to take an I out of there, because whenever you have a negative, an I is going to come out. And then I break this up. Well, this is going to be square root of 4 times the square root of 3 is how I can get square root of 12. And square root of 4 is going to give me 2. And then the square root of 3 is just going to stay. And then typically we rewrite this so that we have the 2i in front. So basically up here I'm going to have 3x minus 1 when I take the square root of the left-hand side. And then on this side I'm going to have plus or minus whatever I get when I take the square root of negative 12, which is going to be 2i square root of 3. Then we're going to bring the 1 over. So we have 1 plus or minus 2i square root of 3. Then we're going to divide everything by 3. So we have x equals 1 plus or minus 2i square root of 3 all over 3. Now, unlike the last example, I'm not going to actually break this up into the two separate parts because I know looking at it right now, 1 plus 2i radical 3, I can't combine those, so I'm not going to be able to simplify it any further. So I'm just going to leave my answer with a plus or minus in it, just like that. So the next method that we're going to talk about is called completing the square, and it's basically a method that you're going to use whenever you can't factor an expression or whenever you want to force the expression to be something that you can take the square root of. So it's called completing the square. And you're going to use it to get something that looks like this. A quantity squared equals a number. So it's a process that you use to force your equation to become in this format so that you can take the square root of both sides. So what you always do first is you're always going to bring the number over to the other side. So I'm always going to bring any numbers to the other side. So I'm going to subtract 9. I'm going to bring it to the other side. So I have x squared plus 6x equals 3. So if you look, you're forcing it to become in this format. So it equals the number. And then what you do is, if you think back to when we multiply binomials, we always draw the box to help us visually see what's happening. So basically what I'm going to do is I'm going to force this to become a perfect square. So I'm going to take x squared, and we know that that would break up into x times x. So those are going to be the sides of my upper box here. And then the next thing I need to do is I need to split this up evenly. So splitting it up evenly means dividing it by 2. So if I take 6 and I need to split it up, it's going to become positive 3 and positive 3. So basically, if you look, if you were to multiply these, this x squared is from right here. And then this is going to be 3x and 3x when you multiply, which would give you that 6x, that middle term. So far, I've created this expression, x squared and 6x, and I created the sides of my box because those are going to end up being the factors. And then whatever number that I multiply and get right here, that's the number that I need to add to both sides of my expression to complete the square. So basically what I'm doing is, if I add 9 to both sides, you end up with x squared plus 6x plus 9 equals 12. And now what you've done is you've created this perfect square trinomial. And essentially, if you look for this particular example, looking ahead or looking back, these actually ended up being the same. That's not typically going to happen, but basically I didn't need to do this whole completing the square step, because I could have just taken this and I could have said, okay, I know that that's a perfect square trinomial. And the reason why I knew that ahead of time is because the first term and the last term are both perfect squares, and the middle term is 2 times the square root of those first and last terms. So whenever you see something like that, you don't have to go through this whole process. I just wanted to go through the whole process to show you how you would get the perfect square trinomial and how you would get the sides of the square. So basically, since this is a perfect square trinomial, what that means is the factors, if you were to factor it, would be x plus 3 times x plus 3, or perfect square trinomial, meaning x plus 3 quantity squared. And I just keep the equals 12. And if you notice, this x plus 3 times x plus 3 are the side lengths of my square. So now I've forced this to become something that I can take the square root of. So now I can take the square root of both sides. I'm left with x plus 3 equals plus or minus the square root of 12, which I'm going to break down off to the side. So we have the square root of 4, square root of 3. So you get 2 square root of 3. And then your last step is going to be just to subtract over that 3. So negative 3 plus or minus 2 square root of 3. So again, if you saw that this was a perfect square trinomial from the start, you could have jumped right from this first step all the way to x plus 3 times x plus 3, or even to x plus 3 quantity squared. But showing you in the square method here, I'm showing you that the number that would have to be added to this was 9 to force it to become a perfect square trinomial. So let's look at some more examples so that you get the hang of the process. So this next example, this is just like a summary here of the steps. But the next example here, we can factor this because you could do add, multiply, add to negative 6, multiply to 5. You could do x minus 1, x minus 5 would work. However, I want to do this by completing the square. So what I'm going to do is you're going to force this to become some quantity squared equals a number. So you always have to bring the number over. So it's opposite of factoring. Factoring, you always want it to be equal to 0. And completing the square, you have to have it equal to the number because in the end, you're going to take the square root of both sides. So now what you do is you're going to draw your square and you split up the x squared, x and x, because if you multiplied those, that would get you x squared. And then you split up the 6x, the negative 6x. So when I split that up, I divide it by 2. It's going to be x minus 3, x minus 3. Because if you were to actually finish multiplying the square out, you would have negative 3x, which would combine to give you negative 6x. So in order to split up negative 6x, you just divide negative 6 by 2, and that's what numbers go on the side of your box. Which actually shows you that this became a perfect square trinomial because these are going to be x minus 3 times x minus 3, or x minus 3 quantity squared. It's going to be the entire quantity squared. And then what you're going to end up doing is you have to multiply those because you have to figure out, well, what number needs to go here so that I actually do have a perfect square trinomial. And the answer is negative 3 times negative 3, so positive 9. And it's always going to be a positive number down here because you're always going to either be multiplying 2 negatives or 2 positives. So then this is going to be the number that you're going to add to both sides. So you're going to add 9 to both sides. So what you're going to be left with on the left-hand side here is going to be your perfect square trinomial. So x squared minus 3x plus 9 would factor down to x minus 3 all squared. It always has to be a repeat factor because it has to be a perfect square, which means the factors are the same. And remember, the factors always come from the sides of the square. And then you're left with negative 5 plus 9, which is going to give you 4. And now I have something that I can take the square root of. So now you can take the square root of both sides. So we have x minus 3 equals plus or minus square root of 4 is 2. Then you can bring the 3 over. And now we have your two cases. We have x equals 3 plus 2, so we get 5. X equals 3 minus 2, so we get 1. So our two answers are 5 and 1, which you could have found also by factoring. So we're going to do some more examples just to get familiar with it. So here's another example. We're going to solve by completing the square. This equation is not factorable, so you would have to solve it by completing the square. So completing the square works when your equation is not factorable, so that's why it's a good method to know. So if we have x squared plus 5x, we're going to bring the 2 over. And I'm going to go ahead and I'm going to draw the square. And I'm splitting up the first term, so this is where the x squared came from. And now I need to split up the 5x. So I need to figure out, well, what numbers are going here so that when I combine them, I get a positive 5x. So essentially, you need to divide it by 2 because this needs to be a square. So when you divide 5 by 2, I'm just going to leave it as 5 over 2. So this would end up being 5 over 2x, 5 over 2x, so that when you combine them, you get 5x. And then the number that you need to add to both sides of this equation so that you create a perfect square trinomial is the number that would go in this box here. So if you multiplied 5 halves times 5 halves, you multiply 5 times 5, gives you 25, and then multiply 2 times 2, you get 4. So we would have 25 over 4 being added to both sides. So it's always, if you look, everything in this square is this polynomial. All of the terms in this square are equivalent to the terms in this polynomial. So that's what you're doing. So basically you're undoing the multiplication process. So if this is all of the terms of the polynomial, you want to know the two factors or the two numbers that you multiplied to get all of these terms. So you would multiply x plus 5 over 2. And then we're going to go ahead and we're going to add this. So we have, I'm going to just do that off to the side, 2 plus 25 over 4. The easiest way to do this is just to think of it as a mixed number, 2 and 25 over 4. And then to solve this mixed number or to combine it, you multiply these and then you add what's left. So we would have 2 times 4 gives me 8. So then it's 8 plus 25 over 4 is what's left. So you would get 33 over 4. Just to review this fraction stuff with you because you do need to know it for your AccuPlacer exam. So 33 over 4. So now I'm going to square root both sides now that I have it as a quantity squared equals a number. So we have x plus 5 over 2 equals plus or minus, and now you have the square root of 33 and the square root of 4. Remember, whenever you're square rooting a fraction, it's like taking the square root of the top and the square root of the bottom. And in this case, my square root on the top isn't going to reduce, so I'm just going to leave it as the square root of 33. But on the bottom, the square root of 4 is just 2. So then I can bring this 5 halves over, so it's going to be negative 5 halves plus or minus square root of 33 over 2. And since these both have the same denominators, I can combine this as x equals negative 5 plus or minus square root of 33 all over 2. Because when you're adding fractions, if you have the same denominator, you can just combine the top. So these problems can become a little more difficult because you have some fractions that get involved, but you really need to know how to do operations with fractions because it's something that you're going to see a lot. So we're going to do a couple more just to keep, the idea going. So we have x squared for this one plus 3x equals 4. I bring the 4 over, so I'm going to draw the square. So draw the square. So we have x and x, and we need to break up. So we have the x squared. So we need to break up the 3x so that when we add them here, we get 3x. So you always break it up by dividing it by 2. So it's always just that middle term divided by 2. So that's the 3 over 2x and 3 over 2x. When you combine those, you get your 3x. So far I have this part of my expression from over here is in the square. And if these are going to be the factors, that means I need to know, well, what number do I need to add to both sides over here so that I can use these as the factors. So you multiply, and whatever number you get is the number you're going to add. So multiply across the top, we get 9. Multiply 2 and 2, we get 4. So that means you have to add 9 over 4 to both sides so that you have a perfect square trinomial so that you can use these side lengths of the square as your factors. So x plus 3/2. And again, the easiest way to add 4 and 9 over 4 is just to think of it as a mixed number. So you would end up with 4 9/4. And then again, you multiply these, and then you add what you get. So to convert into an improper fraction. So 4 times 4 gives me 16, and I'm going to add that to 9. And you always keep the denominator. So this is going to give you 25 over 4. So we have 25 over 4. Now we can square root both pieces. So we have x plus 3/2 equals plus or minus. In this case, you can just square root the top, square root the bottom. They both are perfect squares, so you get 5 over 2. Bring over that 3/2, so it's going to be a negative 3/2 plus or minus 5 over 2. And again, your denominators are the same, so this is going to become negative 3 plus or minus 5 over 2, which then gives you the two separate cases. Negative 3 plus 5 over 2 and negative 3 minus 5 over 2. So we have negative 8 over 2 gives me negative 4. And up top we have 2 over 2, which gives me 1. So those are my two answers. And we have two more to look at where the coefficient is not 1. If you've looked, all of these last examples have had a leading coefficient or the number in front of x squared equaling 1. So we're going to continue doing this where the leading coefficient does not equal 1. So here we can't go right into the completing the square process because we have a leading coefficient not equal to 1. So what you need to do is you need to first see if you can divide everything by that number. So if you divide everything by 3, you end up with x squared plus 4x minus 2 equals 0. And then from there, you can go into the completing the square process. Now remember, if these equations don't specify, like this one says solve for x, so I don't have to complete the square if I can factor it. But unfortunately, you can't find any numbers that are going to multiply to 2 and add to 4. So I have to complete the square. That's the only other way that I can solve it. And keep in mind, completing the square is only going to work for quadratics in the form ax squared plus bx plus c. If you're missing that bx term, you can go right into the square root method, and you don't have to actually complete the square or find the number that would make it a perfect square trinomial. So I'm going to go ahead and I'm going to split up the x squared. And now I need to split up the 4x so that I can figure out how to add those two numbers to get 4x, and they have to be the same number because this has to be a square. So it's going to be plus 2 and plus 2 when you divide 4 by 2. So this would be the 2x and the 2x to combine to give me 4x. And then I have to figure out, well, if I want these lengths to be the sides of my square, what number do I have to add to both sides as the constant, which is going to be positive 4. So we're going to add positive 4 to both sides. So now this is a perfect square trinomial with factors of x plus 2 and x plus 2. And over here I have 6. So now I square root both sides. I get x plus 2 equals plus or minus the square root of 6. Isn't going to simplify, so I'm going to leave it like that. And all I need to do now is just bring over the positive 2. So it's going to become minus 2 when I bring it over. And plus or minus the square root of 6. And one last example. What happens when you have a leading coefficient and it doesn't divide nicely. Well, the easiest way to probably still do this is just go ahead and divide it, but leave things as fractions. So meaning I'm going to have x squared minus 8 over 3x plus 7 over 3x equals 0. And it just means that you're going to have to work with fractions. So I have x squared minus 8 over 3x equals negative 7 over 3. And this is why it's really important to make the connection that the sides of your squares are actually your factors that go here. So I'm going to split up x and x, and I'm going to split up this negative 8 thirds. So you're going to divide negative 8 thirds by 2. So when you divide a fraction by a whole number, this is really like dividing in the number by 2 over 1. You got to keep the first one, so negative 8 over 3, change the sign to multiplication, flip the other one. So it's keep, change, flip. So keep, change, multiplication, flip the bottom, and then you multiply across the top. So negative 8 over 6, which we can reduce. We can take a 2 out of both of those. So if I divide the top by 2, I get 4. If I divide 6 by 2, I get 3. So that means half of this term is negative 4 thirds. Now, you can also think of half of that term as just multiplying by a half, but dividing by 2 is the same thing as multiplying by a half. So that's just the fraction work off to the side here. So inside the box here, remember, this stuff is just, it should always match what's over here. So if you multiplied this, you would get negative 4 thirds x, negative 4 thirds x. If you combine these like terms, you should be getting this, which you do. And then the last thing here is to multiply to figure out what number needs to be added. So it's going to be positive 16 over 9. So multiply the 4's, multiply the 3's. So you're adding 16 over 9 to both sides. So this is just going to become x minus 4 over 3. Because remember, it's always the side lengths of the square. Make sure you remember that, because to try to factor this expression would be a nightmare. So that's the whole reason why we set the square up, so that you remember, well, in the inside of the square is really my polynomial over here. That's a perfect square trinomial, so that the factors are on the outside. And then we have to do that fraction work there. We have negative 7 thirds plus 16 over 9. So get a common denominator. So 9 can be my common denominator. So 16 over 9 is going to stay. So I would have to multiply this one by 3 to get 9. So I'm going to have negative 21 up top. So you're going to do negative 21 plus 16 all over 9. And when you combine negative 21 plus 16, you're going to get negative 5 over 9. So on this side, we're going to have negative 5 over 9. So again, this is just more fractional work. So now I can square root both sides. Equals plus or minus. I'm going to go ahead and pull up the I. Square root of 5 over 9. And you can think of this as square rooting the top and the bottom. So I have I, square root of 5 is just going to stay, but when I take the square root of 9, I get 3. So now I'm going to just simplify this in one more step here. I'm going to bring that 4 thirds over. So I get plus or minus I square root of 5 over 3. And the last step is you can, because these both have the same denominators, rewrite them as one big fraction. So 4 plus or minus I square root of 5 all over 3. So that one definitely has, the simplification becomes pretty complex just because of all the fractions, but that's as hard as these will be.